In this lecture, we will explore the fundamental principles behind wind turbine power extraction and introduce the basic aerodynamic model used for rotor design. By the end of this lecture, you should be able to explain the basic principles of power extraction by a wind turbine, understand the maximum aerodynamic power coefficient of an ideal wind turbine, understand the fundamentals of blade element moment theory for rotor design, explain how various design parameters affect the aerodynamic performance of a wind turbine rotor. As we learned in the previous lecture, a wind turbine is a device designed to extract energy from the wind by converting the kinetic energy of moving air particles into mechanical energy. When designing a wind turbine rotor, we start by defining a distribution of aerodynamic force. At the core of this process is Newton's third law. The force that the rotor applies to the wind is equal and opposite to the force that the wind applies to the rotor. For a wind turbine rotor, the aerodynamic force acts against the wind. As air particles pass through the rotor, their total kinetic energy decreases. This reduction in kinetic energy is converted into useful mechanical energy. Thus, power is extracted from the airflow by slowing down the wind. We use rotors to materialize this forces distribution over space. The representative actuated surface for hot rotor is an actuator disc. The interface that separates the disturbed and undisturbed air is called a stream tube. The power extracted by the rotor is equal to the force applied to the flow, multiplied by the wind velocity passing through the rotor UR, expressed as P equals to F times UR. Let's consider two extreme cases. If the actuated disc moves freely with the wind, it's not resisting at all, the force applied to the wind, F, becomes zero, no power is extracted. So F equals to 0 leads to P equals to 0. If the actuated disc is completely solid, meaning it blocks the wind entirely, then the velocity passing through the disc becomes 0. Again, no power is extracted. So UR equals to 0 leads to P equals to 0. This leads to an important conclusion. There exists an optimal balance between the resisting force and the flow passing through the rotor to achieve maximum power extraction from the wind. Then, what's the maximum efficiency can we achieve for a wind turbine rotor? Now let's look at the streamwise sectional view of the stream tube. The rotor applies a force opposite to the wind direction, causing the wind speed to decrease as it passes through the rotor. In other words, the flow velocity at the rotor plane, denoted as UR, is lower than the free stream wind velocity U infinity. To simplify the analysis, we define the axial induction factor A as the relative reduction in wind speed at the rotor plane. A equals to U infinity minus UR divided by U infinity. This allows us to express the wind speed at the rotor plane as a function of A. So UR equals to U infinity times 1 minus A. Without diving into the full derivation, which involves conservations of mass, momentum, and energy, we can arrive at simplified expressions for two key aerodynamic performance metrics. The thrust coefficient Ct, representing the normalized axial force, and the power coefficient Cp, representing the normalized power output. Importantly, both Ct and Cp depend only on the axial induction factor A, which describes how much the wind slows down as it passes through the rotor. To find the condition for maximum power extraction, we differentiate the power coefficient Cp with respect to the axial induction factor A, is dCp dA equals to 4 times 1 minus A times 1 minus 3A. It has two zero values for A equals 1/3 and 1. The case of A equals to 1 corresponds to a situation where the wind is completely stopped, no flow passes through the rotor, hence no power is extracted. Our point of interest is A equals to 1/3, which gives the maximum power coefficient. As it is shown in the right graph, at A equals to 1/3, we have the maximum Cp, which equals to 16 over 27, approximately 0.59. In other words, the maximum possible efficiency of an ideal wind turbine is 59%. This theoretical limit is known as the base limit, named after a German physicist who first derived it. At maximum power production, the wind speed passing through the rotor plane is 2/3 of the undisturbed wind speed. In other words, the wind speed is slowed down by 1/3 due to the presence of the rotor. To achieve the maximum power extraction, the long-dimensionalized axial force coefficient Ct, it must be 8/9. So how do we achieve such a desired load distribution? We can use blade element theory. If we take a cross-section of the blade, we obtained an airfoil profile. For a given airfoil profile, the lift and the drag forces coefficient depend on the angle of attack alpha, which is the angle between the relative wind direction and the chord line of the airfoil. As we can see from this sketch, the induction factor A and the blade's rotational speed omega influence the angle of attack alpha and thus affect the lift and the drag forces. The lift and the drag forces on the airfoil are functions of relative wind W, angle of attack alpha, and the chord length C. We can project the lift and the drag forces into the rotating reference of the rotor, resulting in an axial force, which is out of plane, Fn, and a tangential force, which is in the rotating plane, Ft. The sum of the axial force from all blades, dFn, times B is the number of blades, from the blade element theory equals to the thrust dt on that swept sectional area of that airfoil sections from the moment theory. By iteratively solving the system equation, we can determine a converged value of the induction factor for a given design. By adjusting parameters like rotational speed, airfoil shape, number of blades, chord length distribution, and others, we can optimize the desired aerodynamic performance. This animation illustrates how design parameters affect rotor performance. By moving the green button, you can adjust key rotor design parameters of rotation speed, number of blades, and the blade chord length. The orange dot then displays the corresponding values of thrust coefficient Ct and the power coefficient Cp for that specific design. As you can see, increasing the rotor speed initially leads to higher Ct and Cp values. However, after reaching a peak value, further increase in rotor speed causes Cp to decline, even though Ct continues to rise. This is because the blades began to rotate too quickly, blocking more airflow and reducing overall efficiency. Similarly, you can observe how changes the number of blades and the chord length influence rotor performance. As you can see, optimal aerodynamic design can be achieved through various combinations of these parameters, as long as the resulting configurations produce a favorable balance between the aerodynamic force on the rotor and the airflow velocity passing through it. In this lecture, we have learned the basic principles of power extraction by a wind turbine. That the theoretical maximum power extraction efficiency is approximately 0.59. The fundamentals of blade element moment theory for rotor design. How key design parameters influence rotor performance.